In this example, we're being asked to use a calculator to approximate each expression in radians rounded to 2 decimal places. Remember that an inverse trigonometric function is going to have an output that is an angle. However, our calculators do not have inverse secant as an operation, so we can't input this directly into the calculator. We do know that this inverse secant function is going to give us an output angle that's somewhere in between 0 and pi, meaning that this angle output is somewhere in the first or the second quadrant. Because this secant value is positive, the angle that we're looking for is going to be in the first quadrant. So let's create a concept drawing to help us understand what we'll need to put into the calculator to determine this angle. We know our angle's in the first quadrant, and we also know that the secant of that angle is 5. Remember, the secant is going to operate on an angle and have an output that is a ratio. And this ratio 5 represents the sides of the triangle that is built from the reference angle. We also know that the cosine of this angle theta is going to be the reciprocal of that ratio. And when we think about the SOHCAHTOA acronym here, the 1 in this ratio has to be the adjacent side, and the 5 in this ratio has to be the hypotenuse side. And we actually don't even need to find this other leg in this particular problem. Because as soon as we're able to express this ratio in terms of cosine, we can actually say, well, inverse cosine is a button on our calculator, and we can operate on this reciprocated ratio to get an angle that's the same. Now remember, we said that secant had an output that's going to be an angle somewhere in the first or the second quadrant, but that's also the same outputs that we get from inverse cosine. So we would also get an angle in the first quadrant if we used inverse cosine, and that's the quadrant that our desired angle should be in. So we can just use inverse cosine of 1/5 to get that angle. Now let's look at it in our calculator. So we do need to make sure that our calculator is in radians for this one. And now we're going to go back to the home screen and input the inverse cosine of 1/5. And we see that we get a small angle in that first quadrant. It's said to round to 2 decimal places, so we'll call it 1.37. So we get that our angle in question is approximately equal to 1.37. We don't put units because it's measured in radians, and this is our angle rounded to 2 decimal places. Now for part B, let's look again at inverse secant of 0.8. Ideally, we would get an angle here in the first or second quadrant. We are going to run into a problem with this one, but let's see what happens. Let's take a close look at this. 0.8 is the same thing as 8/10. Now, we saw a moment ago that we could just reciprocate the ratio and call that 10/8 and try to figure out that angle here. But that would mean that the cosine of an angle is equal to 10/8, and that is a number that's bigger than 1. Remember, the output of a cosine operates on an angle, the output is a ratio, and that output has to be a number that's in between -1 and +1. So the inverse cosine has to have a ratio in between -1 and +1 also. There is no angle who has a cosine that's bigger than 1. And so what we'll say here is that there's no solution to this inverse trig expression. Now here in part C, we have the inverse cotangent, and again, this is going to give us an output that is an angle. And for inverse cotangent, this angle that comes out is going to be either in the first or the second quadrant. Now, we're going to run into a snag here, because if we're looking to calculate the inverse secant of a ratio to get some angle, we can use inverse cosine of the reciprocal of that ratio to get the same angle. And that's because inverse secant and inverse cosine have the same range restrictions, quadrant 1 and quadrant 2. We can use inverse sine on the calculator to help us calculate the inverse cosecant. So the inverse sine of the reciprocal of that ratio is going to give us the same angle as inverse cosecant. And that works out because both sine and cosecant also have the same range restriction, quadrant 1 or quadrant 4. However, we cannot use inverse tangent to get this angle, because if we were to reciprocate this ratio, we would get an angle. I'm going to call it beta because it's definitely not going to be the angle theta that we're looking for. The inverse tangent of a negative quantity is going to give me an angle in the fourth quadrant. And that beta is even going to be measured with a negative value. The angle that we're after, theta, having a negative cotangent, would be an angle in the second quadrant. And so we're going to have to do something different here in order to find it. So let's start with what we know about theta. We know that it's an angle that lands in the second quadrant. We know that its cotangent is equal to negative 2/3. And we know that its tangent is the reciprocal of that ratio, negative 3/2. Because the tangent of an angle is defined to be the y-coordinate divided by the x-coordinate when we're looking at a point on the terminal side of that angle, we can use this ratio to get that point. So our x value is going to be 2, our y value is going to be 3, but because we're in the second quadrant, the x-coordinate has to be negative. Let's also drop a perpendicular in order to make the reference triangle here in the second quadrant. We know that this lower leg is of length 2 and the vertical leg is length 3. So what we're going to do is find cosine theta, which is a ratio between the sides of the triangle, or the ratio x over r once we find that distance our point is from the terminal side. In order to determine this r value, we're going to use the Pythagorean theorem and say 3 squared plus 2 squared is equal to r squared. So 9 plus 4 is equal to r squared. We've got r squared is equal to 13, and therefore r is equal to the square root of 13. And of course, we're only after the positive value because we're talking about the length of a side of a triangle. So now we know that the cosine of this angle is going to be the x-coordinate divided by the value r, which is rad 13. And we can now use the inverse cosine of this ratio to find the angle that we're after that's in quadrant 2. Now remember, the inverse cotangent of a ratio is going to give us an angle in the first or second quadrant. We can use inverse cosine of a different ratio to get that same angle. And we like inverse cosine because the output possibilities in my calculator are the same as the possible outputs for inverse cotangent. We're able to get this same angle in the correct quadrant by just building a triangle and figuring out what ratio we would need to use in order to give us the same angle theta. So this is what we're going to put into our calculator in order to get our angle theta. So back over here, we're still in radians, and we're going to use second inverse cosine of negative 2 divided by square root 13, and then we hit enter and we get the angle 2.16 after we round that to 2 decimal places. So our final answer is going to be approximately 2.16. Again, no units because we're measuring in radians, and that would be our answer.